Hello? Okay. Hello, my name is Peter Lawrey, and I'll be giving a quick talk, which hopefully will be followed by a longer question and answer session on hitting the limits of your hardware with Java. The purpose of this talk is to look at some basic things that you can see in Java where the limit is not your software, but in fact some characteristic of your hardware, be it CPU, memory, hard drive, I/O. Something of my background, I've worked in a number of hedge funds and an exchange designing high-frequency trading systems, and you can often, once you've removed a lot of the layers of your software, you can find that you are actually experiencing some limit due to hardware. And at this point, it's useful to know what that limit is, because you can either, say, upgrade your hardware appropriately, or you can find some other way of changing your code so that you're not using the hardware in the same way. Now, in a system, a common practice to try and improve performance is to increase the number of threads that your system is using. This will work well for some situations. It will make very little difference in other situations, and in some cases, it will just make matters worse. And a lot of it depends on the resource that is your source of your bottleneck as to whether adding more threads will help, make no difference, or it'll make it hinder. So here's an example of what sort of scalability you might expect to get on two different processors. The top one is an i7, the middle one is an i5. Difference being that the top one has 4 cores with hyperthreading, the bottom one has 2 cores with hyperthreading. And in this case, each thread is doing independent work of either floating point or integer. And as you can see, you get reasonably good scalability as you add more threads, up to about 8 threads, which is that middle peak line. And as you add more threads beyond the number of CPUs you have available, you see a small degradation in performance. And in many cases, for CPU-bound processor tasks, the optimal number of CPUs is the number of an optimal number of threads is the number of CPUs you have. Now, this is a slightly different situation. Instead, what I'm doing is just copying data around. So this is very memory intensive. There's not a lot of CPU involved. And what you see here is that you get slight improvement in performance when you have more CPUs, but it's a lot less than you might expect. As you can see, I've normalized here, as in the previous case, there's one thread in one CPU is 100%, and everything else is relative to that. So, for example, in the bottom case, where I'm copying large amounts of data on an i5, you see almost 10% improvement if I use 4 cores instead of 1, 4 threads instead of 1, which is a little bit less than you might expect. You know, if you've split it across 4 threads, but in reality, you're seeing marginally bigger improvement. Now, the thing is that's a bit deceiving about this is if you look at the system CPU usage, you will actually see that the CPU usage goes up. You know, you run it on 1 thread, it uses 100%. You run it on 2 threads, it's now using 200%. You take it up to 400% on Linux. On Windows, it shows it as 25, 50, and 100%. But in any case, your CPU keeps going up. And you think, oh, it must be running faster now. I'm using all of my CPU. But actually, you see very little improvement in this kind of situation where you're just copying data around. Now, there's also a situation where actually things just get worse, and that is when you've got a physical hard drive. With SSDs, you get marginal improvement. You get similar sort of behavior that you get with just copying memory around, which is not too surprising since it's a solid-state disk. But for physical disks, when you start trying to act on multiple portions of the disk at once, you actually cause what was sequential reads or writes to turn into random reads and writes, which actually has worse performance characteristics. So a common question I see on Stack Overflow is, my file system is running slowly. I would like to use multiple threads to make it go faster. And that breaks this fallacy that actually what you might find is that you will go slower, and you're better off just figuring either putting in a faster disk, because they really don't cost that much these days, particularly SSDs, or you just have to live with the performance of your hard drive. So I thought I'd throw in a bit of code here. It's a bit difficult to show all of the code, but in this case, this is the sort of test, the main part of the test harness for all of those tests. What I have is I have an array, you see in the middle of the code, services here. There's an array of services. Each one of those is an executor service with 1, 2, 4, 8, 16, and 32 threads. And then what I do is I pass it in 64 jobs, which will then get split across all of those threads. And I just run the same 64 jobs in each case and time how long it takes. And for the output, I normalize them that the one thread is 100% and then see whether it gets more performance or less performance. Now, this can often be a surprising thing, that a lot of people assume that if you use more threads, you will get more performance. But the problem is that to make something thread safe, you have to get it to do more work. You have to put in locking, you have to put in synchronized, you have to worry about how my caches will talk to each other. And so you can actually see a degradation in performance by using multiple threads if you're not doing it carefully. So here's an example of 3 different ways of getting a histogram of 64 million values, right? So basically I generate 64 megabytes of bytes, random bytes, and then I try and get a histogram, like count of how often each one of those bytes occurs. The reason for doing this is it should scale very well. You should be able to put it across multiple threads, and should see this should be fairly efficient, you would think. So I look at it 3 different ways. One is to have each thread do its own timing, counting, and then have those results be accumulated at the end. Another one is using atomic integers. So there's no locking involved, but it's using atomic integers. And another one uses a global lock, which is an example of the simplest way of doing it, but it turns out to be surprisingly inefficient. So this is the global lock example, where each thread has a start and an end set of data. It goes through, and then using the global lock as a guard, increments the counter. Another one here is doing the same thing, except now it's using atomic integers. It doesn't need to use any locking because the get and increment is an atomic operation. And lastly, this one is each thread has its own local copy of sort of an intermediate result of, in this case, 256 counters. It calculates for its portion what the totals are, and then only at the end it obtains a global lock, which it adds to the sum. So how does this perform? Where's my graph gone? My graph has disappeared. There it is. Now the top line is doing the accumulation. Now you would expect it, since most of the work is performed independently, you should get reasonable scalability, and this is on an i7. And you actually get good scalability up to the number of cores, but not the number of CPUs, which isn't too bad. So you're getting good scalability up to a factor of 4, but it doesn't go all the way and even close to a factor of 8. Now, then there's the using atomic counters. Now, I expected the atomic counters to be not quite so bad, but in fact, it is dramatically worse. It's about 1/10 of the performance of just using one thread to do the entire job. And it doesn't matter how many threads you throw at it, it doesn't seem to get much better either, which is quite poor. And finally, the global lock. Now, synchronized locks generally do very well when you only actually have one thread, because it optimizes that use case very well. But as you get more threads trying to use that lock, its overhead increases. As you can see, it performs very badly if you're doing a lot of locking compared to the amount of work you're actually doing. So in this case, the simplest example is actually just do it all in one thread, and you would actually have been faster than the other alternatives of trying to make it multi-threaded. But there is still a path there where you could have made it faster. Now, slide slightly out of order. This is a comparison between using the accumulated integer and the previous example where every thread was completely independent. And in fact, there's a discrepancy here. It doesn't scale quite as well. And has anyone got any suggestions as to why it doesn't scale quite as well as the completely independent threads? What shared resource is it working on? Yeah? Yes, it's the memory access. Not so much the accumulation at the end, because it's only copying a small amount of data, but the original array. It's a 64 megabyte array. It won't fit in cache, so it actually has to load it off main memory. And all the threads are trying to do this all at the same time. And so that's where you don't get quite the scalability you might get in theory. Okay, this is another example of where this is a very fast producer and a fast but not quite so fast consumer. So the producer in this situation is producing just over 11 million messages a second, but it only does it for the first 24 million messages, right? Which might sound like a lot of messages, but in this situation, it actually comes to a much slower performance after only a couple of seconds of running at this rate. And then it sits there at a much lower rate. Now, you can actually deduce a lot from this graph, particularly if you know the hardware, because 250 megabytes a second, which is the size of the data being written, because each message is 100 bytes each, is, well, for me, it's a kind of a magic number. The reason it's a magic number is that there's some common devices and the sort of throughput that you can expect to get out of them. If you've got hard drive, if you're writing to a hard drive, you can expect to get maybe 50 megabytes a second out of it. If you're writing to a network share on a gigabit LAN, you might get up to 110 megabytes a second. If you've only got 100 megabit, you might get 11 megabytes a second. So if you see like a stream, it's writing out 11 megabytes a second, it's quite likely that you're pushing that data through a 100 megabit line. But in this case, I was getting 250 megabytes a second. Now, as you can see, I've either got an expensive storage array with multiple disks, or I've got an SSD. And in fact, in this situation, I'm actually writing the data out to an SSD. And that's what's causing me to slow down. The reason why it doesn't slow down immediately is because I'm not committing the writes. So in fact, that space where it's running faster is the point at which the buffer hasn't filled up yet. So it's, for the first couple of seconds, it's just filling the buffer as fast as it can. And as soon as that buffer is reached, then you get that slowdown. And you can do other tests on the same hardware and show that the hardware gets that sort of speed with DD and other tools. That's basically the right speed of this SSD. Now, of course, the obvious thing to do here is this SSD is not particularly expensive, or certainly not the fastest that you can get. So a simple way of improving the performance of this scenario is just to put in a faster SSD, say twice the size. Because the reason for that is that SSDs are naturally striped. So the larger the drive, typically the more throughput you will get in with that drive. Okay, so here's a comparison of that same test, except instead I'm writing to tempfs instead of writing to a drive. And as you can see here, it's just going for it. It's not being slowed down by the writes at all. And so any suggestions of what might be slowing me down here? It's I'll give you a hint. It's writing at about 1.5 gigabytes a second. Is there anyone know of any components in a system that's typically around 1.5 gigabytes a second? Sorry? Memory, yeah, or even a PCI bus, because a PCI bus is about 1.5 gigabytes a second in a typical PC. But in this case, I would say it's actually more the CPU and the memory combination. But if you see that kind of number, it's also possibly just the limit of what the PCI bus can handle. Okay, so we're down to the questions and answers already. Has anyone got any questions? No? Yeah?
So if you have separate threads dealing with different data,
Yes.
doing something at the end once they're all finished, would you expect to see the same kind of memory bottleneck?
Potentially. It depends on how much. In the example I gave, it's not doing very much work with each piece of data. So the bandwidth is actually an issue, the memory, how fast it can suck the data out of main memory. If you're doing quite a lot of work with each piece of data, even just a multiplication, certainly division even, then your CPU load goes up for each piece of data. And then suddenly you're now got a CPU bottlenecked task. And so then you start to see the sort of scalability that you should expect. But it is easy to underestimate how limited your memory bandwidth is. You might expect to get, say, 3 to 6 gigabytes a second from your main memory into your CPU. Now, the thing is that you have a system with a clock speed of, say, 3 gigahertz. So that means in each clock cycle, you can, on aggregate, read about 1 byte. Right? So that's across all of the threads. On aggregate, they can only be accessing 1 byte that's come out of main memory. So you can see how limited that resource can be, and how much it can restrict your ability to use every CPU on your core. Yeah. Sorry? Sorry? It excludes paging activity. Includes paging activity. Yes, that will just make the matter worse, yes.
Do you have any advice on, in general, how to measure this stuff? Because it's pretty gross. I don't know.
Yes. Well, I can show you the code for it. Most of the code is very simple. It's simple enough that it doesn't get optimized away completely, but hopefully complicated enough that it will do something, put some stress load. So, for example, in the CPU computation, in the floating point case, it did the same thing except with doubles instead of longs. In the case of the memory copy, I just took an array and did a copy to another array of the same size, just to see how just shuffling data from one place to another. It's similar to accessing a data structure of round about the same size and then copying it to another data structure. So you're doing a combination of reading and writing. The disk activity is a little bit more complicated because in Java you can't control what's in memory and what's on disk. So you have to, in that test, what I did is I created a file that's the same size as the main memory. That's not. So, okay. So for the fixed point test, it just does this. Okay, so in this case it has a complex number, just random piece of computation. It has a complex number which it just multiplies by itself 100,000 times and returns that so that it won't be optimized away, and times how long it will do that. Now the thing is, each thread can act completely independently because the object involved will fit into the cache of each CPU quite readily. It has a starting value, but from after the first value is started, it will they'll be local to each thread. Floating point is basically the same. So in the case of an individual application, you can do the same idea. You can run your code. You run it first without, hopefully, depending on how complicated your application is, you run it first as a single-threaded application without any locks and doing all the things that it has to do. And then you put your locking in and run it now across, say, 2 or 4 threads and see how much performance improvement you get. Like, does it run a certain amount of work in a shorter time or not? And you can't just assume just because you've now used multiple threads that it will actually be shorter. Because in some cases, you'll be bottlenecking on a resource that it doesn't scale, or because you've added so much overhead by using these multiple threads that you actually run slower. And you've added complexity as well. So you need to test your base case, which is running the same thing, just single-threaded. And then use that as your comparison.
Is there a way do this in such a way that I don't have to go right all the boilerplate every single time I want to test one functionality? So you've got a lot of looping here and a lot of
Is there a way you can make it more general?
And even when I go change my code, is there a way to not have to go and do all this again?
Yes, I see what you mean. The way I usually do it is I just have some simple test that runs the whole thing. I mean, you can use a tool like Calibre, for example, which will give you a set for a particular piece of code. What you really want, though, is to know whether your code scales. And I don't know of any library that will do that. But I showed you what the code was. But it's only about 12 lines of code. And once you've written it once, you can apply it to all of your tests. So that's what I've done here. All of the tests use that same piece of code again and again. Any more questions? Yeah?
Let's say I think that the performance problem, but I don't know if it's main memory metrics or if it's something else or what. Like, don't know at all.
Yes.
Are there any tools that can tell me sort of how much reach, what fraction of each performance I need to know?
Yes, there are, but they themselves can be quite complicated to use. I would suggest that it's actually easier to just see how your system scales. So you start off with a small number of requests, much lower than you want to crank it up to. And then you build it up slowly and see how either your latencies go up dramatically or your throughput improves or your CPU consumption goes up. And then you can see at what point you start to run into issues. And then you can look at your system and say, well, I know my hard drive can write 250 megabytes a second, for example, because you've tested that independently. It's only writing 10. That's not the issue. I can see, for example, that essentially what you have to do is you have to stress test it and see what will impact it and slow it down. Another thing I've done is artificially increase the load on a particular thing. So write one of these tests that's churning the memory and see whether that's slowing it down or not. And if it does slow it down, then the memory can be cause of your problem. If it's not slowing it down, then it's not the issue at all. But it's also, you can look at the scalability profiles. If you're getting good scalability as you add more CPUs, then there probably is CPU bottlenecked. That's assuming you don't really know what your code's exactly doing. But sometimes you also have a feel as to whether you're actually doing a lot of memory activity or you're doing a lot of computation. So hopefully that will also guide you in the direction of which you want to test the code to sort of see where the bottleneck is. You know, to confirm your own ideas as to what the bottleneck probably is. Yes.
So in your earlier, like, 10FS,
Yep.
you said your memory bottleneck, but 1.1.5 gigabytes a second seems like a bit of a low number to be memory bottleneck. So from what I know, I can get sustained object allocation rates of about 4.5, 5 gigabytes a second on my i7 laptop.
Yes.
And Core 2 Duos seem to top out at sustained object allocation rates, like just below a gigabyte. So 1.5 gigabytes a second seems like a bit of a weird, bit of a weird in-between angle.
Yes.
Anything else that's going on?
Well, it is also serializing and deserializing the objects in this case. So when I say memory, it is actually placing lots of data into those cells in the memory location. So yes, it is a sort of an odd number in that sense, but that's because I'm not just initializing blocks of data. One of the things that a lot of messaging solutions test is they test how quickly they can send a very small byte array around, for example, or a large byte array. And they sort of ignore the whole serialization issue. So in a lot of the tests I do, I try to say, well, it's given I have real data, and I hopefully always will have, try and put in something pseudo-realistic in terms of the serialization. But that means that you're placing pieces of data in a row rather than, say, using some very efficient way of zeroing out memory or just allocating a block.
Yeah. The other thing I was going to ask was, in your memory writing examples, are you doing anything at all to make sure your reads and writes are cache line aligned, or whether they straddle cache lines? Because I have seen some getting some numbers suggesting there's quite a significant difference in memory read-write performance
Yes.
on mid-aligned access and straddling access.
Yes, in this case, it is straddling them, but it's writing them continuously in memory. So since they're all written sequentially and not pushed out to disk, it's sort of, I think the difference might be somewhat notional. Okay. In the sense that it's writing 100 bytes at a time and then another 100 bytes at a time after it. And is that different from, say, writing 200 bytes or something that is aligned? Because it's a loop inside another loop, if you see what I mean. So the inner loop is writing 100 bytes, the outer loop is writing that multiple times.
It does make a difference where the flash comes.
There is a memory barrier, but there is no actual flush to disk as such. Right. Yes.
That does make a difference on throughput, and just based on if you are not only aligned, but how full you are, or if you spill over. So if you're smaller than a cache, it's faster than if you're the same size as the cache, and that's definitely, that's faster than if you spill.
Right. Yes. It doesn't look at the alignment. Um, Mainly because I assume that in a realistic case you won't be able to, say, limit yourself to, say, 64-byte messages. So I've picked a number of 100, which is still a round number, but it,
One thing you can do is you can pad
yes.
make sure you get that alignment. But obviously, padding again is to away your bandwidth, so it might be worth something.
That's right. Because the ultimate limiting factor is your speed disk. Disk speed.
Padding doesn't do away the bandwidth because it's the cache line, it's the unit. Yes, sorry, yes. If you're padding to that cache line, sorry. But
Yes.
even so, it's still the unit as a transfer. So you're going to consume bandwidth to the cache size of the cache line.
Yeah. Yeah, in this example, the disk is ultimately your limiting factor. So if you turned every 100-byte messages into 128-byte messages to be, say, 2 cache lines, you would actually be slowing you down in the long run. It would be faster to start with, but slower in the sustained. So then again, there's a trade-off there. It's like the option that will speed up your memory when you're in memory, if that's your limiting factor, is an option that will slow down your disk when if that's a limiting factor. Any more? Yeah.
I think it's interesting about the topic with the cache line misses.
Yes.
Is it possible to know at a method level whether the method is efficient or not by seeing if you're having a lot of cache line misses? So that when you start writing a class, or I don't know if that's the way to start, right?
There are tools coming out that have that kind of detection, but generally in the past what I've done is just looked at it empirically. So if you have a small enough data size, then you will know that it should, after it's warmed up, all be in, say, the L1 cache. And then what you can do is look at how that slows down as you increase the data set size. The problem is, how is that performing in a real application? And so you're starting to sort of guess then, unless you've got some sort of proper tool that will give you your cache miss rate. But I don't think even sort of tools that are coming out will give you on a method by method basis.
That must be really hard because the compilation and optimization is very
No, it's definitely the caches themselves know sort of their miss rate, and how they're optimized shouldn't make too much difference, I don't think, unless, if you've got multiple reads which get turned into one read, that will change what appears to be your hit rate. But generally, if you've got reasonably optimized code compared to heavily optimized code, you might not see much difference, I wouldn't expect.
Would you recommend writing smaller methods, shorter methods? Because you have the probability of hitting less cache line misses with methods that are more concise than having long. It sounds like a.
I would suggest making smaller methods just because they're easier to read and understand, rather than worry about the performance of them. But you're right. Your smaller methods do tend to get optimized better. Simpler methods get the JIT can sort of reason and optimize for them much more efficiently than complex or obtuse methods. And certainly once it gets to a certain size, I think it's quite large, about 8K, it won't even optimize it at all. It just leaves it interpreted. The method is too large by default. Okay. Well, I think that's about it. Thank you.